Welcome, welcome to Chapter 3, Unit 7, Rational Functions. So we have two toolkit functions that are rational functions. It's 1 over x and 1 over x squared. Notice that this is 1 over x squared, and this is 1 over x. One way to distinguish them is that when you look at 1 over x squared, you will not be getting any negative y values. And that's because whatever your x is gets squared. So it will always be positive. Okay, so first thing we're going to talk about is arrow notation. So we're going to use arrow notation to show that a variable is approaching some value. And by arrow notation, I mean these guys. So notice how there's arrows in the middle of all of them, arrow notation. Now we're going to go through them. So here, as x approaches a, when you have a little negative in that top, so let's say we had a here, all of these values would be that positive, and all of these would be that negative. So you can think of this as x approaching a from the negatives. But really, it's x approaching a from the left because it won't necessarily always be negative. So if your left is your negative, obviously your right is your positive. And we're going to talk about here. 1 over x will display this. So notice when we take x approaches 0 from the left side, so from that negative side, what do we get? Well, we're going to say that, we're traveling along here. So we're going to look as we're coming this direction to A. And so as x approaches 0 from the negative, y will approach negative infinity. But notice as x approaches from the right, the positive side, your y will approach positive infinity. So it's not the same. There can be two completely different approaching values depending on where you are approaching it from. So you all are familiar with x increasing without bound. So as our x value shoots off really, really big to infinity, and as x decreases without bound, our x value shoots off towards negative infinity. Here, remember your f of x equals y. So this notation would indicate that your y values are shooting way up or your y values are shooting way down. And here they would be approaching A. And this is special. And you will go over that a little later, but do keep in mind, because what is special to this is that you can get two different approaching values depending on which side you're coming from. That's important. So now we're going to talk about asymptotes. So an asymptote is something that that your graph will get incredibly close to, but it will never reach. So notice here that the y-axis, it never reaches that y-axis. And notice here also that it never reaches that y-axis. That would be a vertical asymptote, the line x equals a. Here it would be x equals 0. And you can abbreviate it saying vertical asymptote, VA. So that means that as our x values, as our y values increase or decrease, it will tend towards a certain value, but it will never reach that certain value. You can also do the same, that is again a vertical. You could do the same thing with horizontal. Notice we have one here, and on this graph we have one here. And this also coincides with the fact that your x on the bottom can't equal 0, or else it's not defined. So you'll have a vertical line, y equals b. So you'll have this vertical line, y equals b, as your horizontal asymptote. Okay, so we're going to try number 2. We're going to sketch the graph and find the horizontal and vertical asymptotes of the reciprocal squared function. That has been shifted right 3 units and down 4 units. So that would be 1 over x minus 3 squared minus 4. So if we're starting, this weird one is x squared. So if this was our vertical asymptote and we're starting here, and we see that we have 1, 1 and 1, 1 on the graph, now we are going to have, when x equals 1, we will, let me see, 1, 1, 1. So this is what we have. And of course, that's a very crude drawing. It can be difficult to draw these things. Now, I am going to take the minus 3 first. So I'm going to shift that right 3 units. So we're going to go from 1, 1 to 2, 1 to 3, 1 to 4, 1. So now we're going to have something like this. And this will go from -1 to 0 to 1, 1 to, let me see, that's 1, 2, 3 to 2, 1. And that's what we have. Now we're going to move it down 4 units. So that's going to go from 1 to 0 to -1. So that's 1, 2, -1, -2, -3. So it is going to be something like this. Now, notice what they want you to notice. Is that here, this is x equals 3. And this is would be that 4. Yeah. Okay. So notice that our asymptotes moved with it. So now what we have is, since we can't have 0 on the bottom, we know that x can't equal 3, which is why we have an asymptote here. And we also know that we can't have a y that is less than 0. So this has got to be either 0 or greater, or actually it's got to be 1. 1 or greater, not equal to 0, greater than 0. And that's because we will never reach 0 here, ever at all. So for the y values, we cannot have it be 4. And that's a horizontal, asymptote. There we go, equals 4. This is a horizontal asymptote, and this is a vertical asymptote at x equals 3. And this can get super confusing, don't worry, I'm not really gonna have you graphing a super whole lot of these. There will be graphing on the exam though, so, and that you're not allowed to use Desmos, you gotta do it by hand. And then scan it and send it in. So now moving on, solving applied problems involving rational functions. So a rational function, notice, as you have noticed, is a function that looks like a fraction. P is the top, Q is the bottom. So P is our denominator, Q is our denominator, P is our numerator. And notice that they're just polynomials. So it's the quotient of two polynomials. And what that means, it's like when you divide two polynomials. So that's what we were doing before. So here is a try it. There's 1,200 freshmen and 1,500 sophomores at a pep rally at noon. After noon, so 12 p.m., after 12 p.m., 20 freshmen arrive at the rally every 5 minutes, while 15 sophomores leave the rally. Find the ratio of freshmen to sophomores at 1 p.m. Okay. So what we're going to look at here is we have got freshmen are 1,200, sophomores are 1,500, and that's what we have at noon. So afternoon, 20 freshmen arrive at the rate every 5 minutes. So every 5 minutes, you get 20 freshmen. While 15 sophomores leave the rally. They 15 leave every 5 minutes. So we're going to find the ratio of freshmen to sophomores. So what we're going to do is we're going to end up with some type of function that is a polynomial here. Now, if we start out with 1,200 students, and these relationships can be expressed linearly as a line, right? Because it's just a solid rate of increase or a solid rate of decrease. So if it's 20 every 5 minutes, and this is 15 every 5 minutes, then I'm going to say that t is equal to a 5-minute increments. So when t equals 1, that's 5 minutes. When t equals 2, that's 10 minutes, and so forth and so forth. And that's how I'm going to reason with this. So my t is going to go from, like 0 to whatever numbers. So keep in mind when you set your increments, it doesn't necessarily have to be something crazy like that exact increment. You can do that. Just like we did for years previously. So if the freshmen are going to be 20 every 5 minutes, that's 20t. And remember, they're going to be coming in at a rate of 20 every 5 minutes. So it's going to be positive. Plus 1,200. And this is the number of freshmen after t minutes. Now, 15 leave every 5 minutes for the sophomores. So they're leaving. That's going to be negative. So that's what we're going to have. And the ratio is just going to be this. So now I start simplifying. So I'm going to take out 10 here. I'm going to take out 20. So that gives me t plus 60. And then here I'm going to take out I can either take out a 5, a 3. Can't really take out a 10. I'm going to go ahead and take out a 5. So that's, and I will rearrange them. So this is going to be 300 minus 3t. And then I can divide these, which gives me 4. And I'm just going to go ahead and multiply that in. 4t plus 240 divided by 300 minus 3t. And this would be our function of the ratio of freshmen to sophomores. Now, if they want it at 1 p.m., so that's 1 hour, that's 60 minutes. So how many 5-minute increments is that? So that's 10. So that's 12. So that's going to be our t. So f of 12 is going to equal 4 times 12 plus 240 divided by 300 minus 3 times 12. And 3 times 12 is 36. And then we have 48 plus 240. And that gives us, oh my gosh, 288 over, let me see, 330 minus 30 is 270. And so we have 264. And then, of course, you can simplify, blah, blah, blah. So it looks like we have slightly more freshmen. Now, finding the domains of rational functions. The domain of a rational function is It would be all of the x values we can have that give us a good y value. So for example, if we had 1 over x, so our x can be anything other than 0. And that would be our domain. Because when it is 0, we get 1 over 0, and that doesn't give us a good y value. So when we look at the domain, we need to first look at the bottom, because we need to look at what x values we absolutely cannot have. So for this one right here, obviously x cannot equal 1 and x cannot equal 5. So now we need any x value that gives us a 1 up top. Hold on. Oh, here, yes. So any value of our top function that makes our bottom function 0 is we're not going to include. So the top function has the domain of all real numbers, but we know that our bottom function cannot equal 1 and cannot equal 5. So our domain is negative infinity, 1, unioned with 1, 5, unioned with 5, infinity. And that's how it would go. And these would produce asymptotes, which we will talk about right now. So when we examine a vertical asymptote, and remember a vertical asymptote is one that goes up or down, we look at the factors of the denominator, that's the bottom, that are not common to the factors in, this should say numerator. Vertical asymptotes occur where the uncommon factors of the denominator are 0. So that means that if you are able to cancel anything out, you can, and then you look at that to determine vertical asymptotes. So cancel first, then look at asymptotes. So we have to factor this. It looks like 2x squared plus 5. That'll give us complex numbers. So I don't have to worry about it sharing any factors, so I don't have to worry about it canceling out. So now I have to factor this negative x squared minus x plus 2. So that gives me negative 2 and 1. So if I factor this, it is going to look like negative x squared minus 2x plus x plus 2, and that gives me negative x plus 1, x plus 2. So I'm going to get 1 minus x and x plus 2. And that will give me my factors. Now notice that I can pull out a negative to switch this around. So the vertical asymptotes, we're going to get 5 plus 2x squared, negative 1, x minus 1, x plus 2. Notice the vertical asymptotes will be x is equal to 1 and x is equal to negative 2. Those are our vertical asymptotes. So that's where the graph will equal 0 on the bottom and it won't count. Sometimes we will have a graph that has a hole. So it will appear to look like a normal graph, except there will be that infamous open circle. This is called a removable discontinuity. And it's called a removable discontinuity because it will be a common factor among the numerator and the denominator. So when you factor anything out, anything that does cancel, you do need to write that on the side because that is a removable discontinuity. There will technically be a hole there when you zoom in super, super, super close. And remember, we're on the real number line, so these decimals can just keep going forever. So it's it's literally just a pinpoint hole right at that number. So we're going to find the vertical asymptotes and removable discontinuities. So this one, obviously, I know is just going to be x minus 2. This has the form x squared minus some number squared. Well, a is equal to 2 here. So then that gives us x minus a, x plus a. So we get x minus 2, x plus 2. So notice that these guys are a removable discontinuity, and this is a vertical asymptote. So vertical asymptote is where x equals negative 2, and a removable discontinuity is at x equals 2. And that's what is meant by that. How many sections do we have here? Okay. So let's see how long. All right, so I'll just go a little bit longer. Okay, identifying horizontal asymptotes of rational functions. Now we're talking about horizontal asymptotes. So 3 things can happen for a horizontal asymptote. So if the degree of the denominator is greater than the degree of the numerator, then there is a horizontal asymptote at y equals 0. And I'm going to show you what I mean here. So if the degree of the denominator, that's the one on the bottom, is greater than the degree of the numerator, that's the one on top, then we're going to have an asymptote at y equals 0. So that means if our function on the bottom is greater in degree than the function on top, we're going to have an asymptote at y equals 0. So like this. Y equals 0 will be our horizontal asymptote. And we can see this. Notice there. I can zoom in for you guys. That is 2, that is 3. The degree of the denominator is greater than the degree of the numerator. Now we can zoom out a little bit. Okay, and we're going to go on to this one. If the degree of the denominator, the one on bottom, is smaller than the degree of the one on top, you're going to get an oblique asymptote. And we will use long division to find the equation of that slant line. So which one does that look like down here, A or B? So it looks like this one, because notice that our top is 2 and our bottom is 1. So the degree of the denominator is less than the degree of the numerator by 1. Exactly 1. So I'm going to go ahead and divide those out to get the answer. And we get it looks like I can divide by -2 using synthetic division because this one is in the form x plus or minus some number. 1, -4, 1. I'm going to bring it straight down for a 1. This gives me -2. This gives me -6. This gives me 12. This gives me 13. If this was x squared, this is now x. So I have C and R. So I'm going to have x minus 6 times x plus 2 plus 13 over x plus 2. So our slant asymptote. So our slant asymptote will be this guy. And that's y equals x minus 6. Now, if the degree of the denominator, the one on bottom, is equal to the degree of the numerator, the one on top, then we have a horizontal asymptote at the ratio of the coefficients. So what does that mean? We're going to look at A to find out. So notice we have the same degree on top and bottom. So we are going to take the ratio of just their coefficients. So 6 divided by 2 is 3. So this is a slant asymptote, and this is a horizontal asymptote. Notice slant asymptote is a line. It's slanty. A rational function has y-intercepts where x is equal to 0 and has x-intercepts where the numerator is equal to 0. Okay. So first we'll look at x-intercepts. So that's setting the top one equal to 0. So we're going to get x is equal to 2 and x is equal to -3. So the x-intercepts are going to be 2, 0, -3, 0 so far. So now let's look at y-intercepts. So that's where our x's are equal to 0. So notice that we have y-intercepts at, if x is equal to 0, 0, 0, let's set this equal to 0. So 0 minus 2 is -2, 0 plus 3 is 3, 0 minus 1 is -1, 0 plus 2 is 2, 0 minus 5 is -5. So now we're going to have -6 over -5 times -1 is just +5 times 2 is 10. So that's -3 over 5. So we will have a y-intercept at 0, -3 over 5. And those will be important in graphing a function. So I'm going to go ahead and stop here, and I'm going to save graphing rational functions and writing rational functions for the next video because I have a feeling it might take a while. So I will see you guys in the next one.